Welcome to the deep dive. Today we're taking a deep dive into the world of particle physics.
Oh, very
We're
cool.
going to be exploring the search for a particle so elusive it's been dubbed the supersymmetric tau, or
Hmm.
S for those of you who like their science,
Hmm.
with a side of Greek letters.
Right.
And you've shared some really intriguing research on how future particle colliders, which are these incredible machines that smash these subatomic particles together at incredible speeds,
Yeah,
could be the key to finally uncovering this hidden piece of our universe.
absolutely. It's a bit like searching for a whisper in a cosmic hurricane,
Right.
but the payoff could redefine our understanding of, well, everything.
Now, I have to admit, when I first dove into this research,
Mhm.
I felt a bit like I was entering a whole new dimension. So,
Sure.
for those of us who might not have a PhD in particle physics,
Right.
let's start with the basics.
Uh-huh.
What exactly is the supersymmetric tau, and why is it so important?
That's a great question. So to understand the tau, we need to talk about supersymmetry, or CSY for
Right.
short. And it's a theory that attempts to answer some of the big unsolved mysteries of the universe.
Mhm.
Things that the current reigning champion of particle physics, the Standard Model, can't quite explain.
Okay, so the standard model, that's like our current best understanding of how the universe works
Exactly.
at the smallest scales,
Yep,
right?
it is, exactly.
But it has some gaps, some head scratchers it can't explain.
Exactly. Things like the existence of dark matter, which we can't see but know is out there due to its gravitational effects, or why the Higgs boson, the particle that gives other particles their mass, has the mass that it does.
Right.
Supersymmetry comes in to potentially fill those gaps.
Okay, so how does it do that? What's the basic idea behind supersymmetry?
Well, in a nutshell, SUSY proposes that every known particle in the universe has a partner particle, a supersymmetric twin, so to speak.
Okay.
These superpartners would have slightly different properties,
Hmm.
and their existence could explain some of the phenomena that the Standard Model struggles with.
Fascinating. So it's like every particle has a secret sibling we haven't met yet.
Right.
And one of these super siblings, these hypothetical particles, is it's the supersymmetric tau.
Right.
What makes it stand out from all the other potential supersymmetric particles?
Well, the Q's is thought to be the lightest of these supersymmetric particles,
Okay.
which has some interesting implications.
Okay.
First, if it exists, it might be the easiest to create in particle accelerators.
Mm.
And second, if it is the lightest, it implies that it can't decay into other supersymmetric particles.
Yeah.
It has to decay into standard model particles that we already know about.
So potentially easier to create, but harder to spot because
Yeah.
it decays into something else.
Exactly.
That sounds like a fun challenge for physicists.
It is.
It makes you wonder if we could somehow gather all these super partners together. Would we have a super periodic table?
There are indeed charts and diagrams that physicists have created to visualize and categorize all the predicted supersymmetric particles and their properties.
Wow,
It's a fascinating way to think about a possible mirror world of particles.
that's incredible. Okay, so we have this theoretical framework, this idea of supersymmetry and its cast of hidden characters.
Right.
But the big question is, how do we actually find these particles?
Yeah.
They don't exactly show up on your average telescope, do they?
You're telling me telescopes aren't really designed for spotting these tiny particles, are they? To catch something as elusive as the Caris, we need something way more powerful. We need particle accelerators,
Right.
sometimes called atom smashers.
Right.
These machines accelerate beams of particles to near light speed and then smash them together.
Yeah.
The resulting energy bursts can create new particles, some of which might have existed for only a fraction of a second after the Big Bang.
So it's like recreating the conditions of the early universe just on a much smaller scale
Exactly.
to try and catch a glimpse of these fleeting particles.
Yeah.
And we're hoping that one of those fleeting particles will be
Yeah.
the power.
Right, exactly.
Yeah.
Now, we already have some incredibly powerful particle accelerators, like the Large Hadron Collider, or LHC, which has been making headlines for years now.
Right.
It's already achieved groundbreaking discoveries, but the search for supersymmetry, and specifically the two, continues.
So we're still looking for that definitive evidence, that aha moment.
Right.
And that's where the research you shared comes in. Right.
Exactly.
It focuses on the potential of future colliders, specifically the International Linear Collider, or ILC.
Right.
What makes the ILC different from what we have now, and why is it so well suited for this particular search?
The ILC is a different kind of beast altogether.
Okay.
Unlike the LHC, which is a circular collider, the ILC is designed to be a linear collider.
Yeah.
Imagine two straight tracks where electrons and their antimatter counterparts, positrons, are accelerated to incredibly high energies and then slammed into each other head-on.
Head-on collisions at near light speed. I can only imagine the energy involved.
Yeah,
But why linear? What's the advantage of that design?
that's a great question. Linear colliders like the ILC have some key advantages over circular colliders,
Okay.
especially when it comes to precision. In a circular collider, the particles lose a bit of energy each time they go around the bend,
Right.
which can make the collisions a bit messy from a physics perspective.
Right.
Linear colliders avoid this energy loss, allowing for much cleaner and more precise collisions.
So it's about getting the cleanest possible data, the clearest signal from the noise of all those particles colliding.
Yeah,
Because we're not just looking for a needle in a haystack here. We're looking for a very specific type of needle.
exactly. And that's another area where the ILC shines.
Okay.
It's designed to be incredibly sensitive to the types of particles that supersymmetry predicts, including our elusive DES.
Okay.
The research you shared highlighted that the ILC could potentially detect the TESS in a much wider range of masses than current experiments, even if it's much heavier than we think.
Okay, so wider mass range, that's like casting a wider net.
Exactly.
But how does it do that? What makes the ILC so sensitive?
It's a combination of factors, but one of the key ones is the ILC's ability to use something called beam polarization. Now, this might sound a bit technical, but bear with me because it's actually quite fascinating.
Okay.
Imagine light waves, they can vibrate in different directions.
Right.
Polarization is essentially filtering those light waves, so they're all vibrating in the same direction. Like, polarized sunglasses only let through light waves vibrating in a specific direction.
Okay, so we're talking about manipulating light waves.
Right.
But how does that apply to particle beams in a collider?
Well, we can actually polarize particle beams too, meaning we can align the spin of the particles, a quantum mechanical property of particles, before they collide.
Okay.
At the ILC, both the electron and positron beams can be polarized independently, giving physicists incredible control over the collisions.
So we're lining up the particles, these tiny subatomic spinning tops, in just the right way before we smash them together.
Yes.
But why is that so important? What does polarization give us that we wouldn't have otherwise?
Polarization is incredibly powerful because it allows us to fine-tune the types of interactions that happen in the collisions. For example, by polarizing the beams in a certain way, we can enhance the production of supersymmetric particles, like our MISS,
Right.
while simultaneously suppressing the production of background particles that we aren't interested in.
Okay.
It's like turning up the volume on the signal we want to hear while turning down the volume on all the noise around it.
It's like those noise-canceling headphones, but for particle physics.
Exactly.
So with beam polarization, we can increase the chances of producing the cue and also make it easier to spot amongst the collision debris.
Right.
But even with all of this, it sounds like finding the two is still a major challenge.
It is.
What are some of the specific hurdles that researchers have to overcome?
You're right. Finding the two is definitely one of the toughest challenges in particle physics today. One of the big ones is dealing with what we call beam-induced backgrounds.
Okay.
Even with something as precise as the ILC, when those electrons and positrons collide, they don't just produce the particles we're looking for. They also create a whole zoo of other particles, some of which can mimic the signals we'd expect to see from a LORD.
So it's like trying to find a single firefly in a fireworks display. How do you even begin to separate the signal of a toucher from all of that background noise?
Yeah, that's where the design of the ILC's detectors becomes crucial.
Okay.
These detectors are designed to be incredibly precise and hermetic.
Okay.
That means they surround the collision point as completely as possible to capture every single particle that flies out from the collision,
Wow.
even those trying to escape at extreme angles.
No escapees allowed.
Okay.
So it's like having a high-speed camera that can track thousands of particles at once.
Yes.
But even more complicated than that.
Exactly. And the ILC's detectors can measure the energy and momentum of these particles with incredible accuracy,
Okay.
allowing physicists to reconstruct the events and identify the particles involved.
Mm-hmm.
The combination of precise detectors, powerful analysis techniques, and of course beam polarization gives the ILC a real fighting chance in the search for the...
It really is remarkable, the level of ingenuity and collaboration that goes into these experiments. It's like global effort to decode the universe.
It is.
So if we're fortunate enough to find the CO, what are the implications? What could this tiny particle tell us about the universe? that we don't already know?
Finding the chive would be huge. For starters, it would be the first direct experimental evidence for supersymmetry,
Right.
which would be a monumental discovery in physics.
Right.
It would mean that our understanding of the universe at its most fundamental level is incomplete.
Right.
And it would open up entirely new avenues of research for decades to come.
It's like opening a new chapter in the textbook of the universe.
Yeah.
What are some of the big mysteries that supersymmetry could potentially shed light on?
Well, as we touched on earlier, one of the biggest mysteries is the nature of dark matter.
Right.
Some supersymmetry theory suggests that dark matter could be made up of these supersymmetric particles, and the C, being the lightest, could be a window into that hidden world.
Okay.
And then there's a problem of the Higgs boson's mass. Supersymmetry offers a solution to that problem as well.
So this one particle, the chwith, could be the key to understanding some of the most profound mysteries of the universe.
It's amazing how interconnected everything is at that fundamental level.
It really is, and that's what makes this research so exciting. The search for the tree and other supersymmetric particles isn't just about finding another particle to add to our list.
Right.
It's about potentially revolutionizing our understanding of the universe and our place within it.
It makes you realize that we've only just scratched the surface of what there is to know. Thank you so much for taking us on this incredible deep dive into the world of particle physics and the search for the chef.
My pleasure.
I have a feeling this is just the beginning of an amazing journey of discovery.
I think so too.
That's it for our deep dive this week. Be sure to check back with us next time when we'll be exploring another fascinating topic. Until then, keep those questions coming and never stop exploring.